Hi, I'm Eugene, a Garmin product trainer. In this video, we're stepping into the world of decompression diving and taking a closer look at the conservatism setting on your dive computer. I've divided this topic into 4 sections: M values, gradient factors, GF99, and surface GF. Garmin dive computers use the Bühlmann ZHL16C decompression algorithm. Bühlmann is the name of the developer. ZH stands for Zurich. L stands for linear. 16 refers to the 16 theoretical tissue compartments used to model how different parts of the body absorb and release inert gas. For example, blood absorbs and releases gas relatively quickly, while joints do so much more slowly. And C is simply the version designation. Version A is used for research, version B for printed decompression tables, and version C for dive computers. Decompression sickness occurs when ambient pressure decreases and dissolved nitrogen in body tissues forms bubbles, which can block blood vessels or damage tissue. The purpose of decompression stops is to prevent this from happening. Let's use this chart to explain how it works. The horizontal axis represents ambient pressure. On the far left is surface pressure at 1 atmosphere. As we move to the right, pressure increases, which means depth increases. The vertical axis represents the inert gas pressure inside a tissue compartment, in other words, the amount of nitrogen accumulated in that tissue. This line represents nitrogen saturation. As pressure increases, nitrogen enters the body's tissues until it eventually reaches equilibrium. If we then ascend and reduce the pressure, the nitrogen becomes supersaturated. Once that supersaturation reaches a certain point, the dissolved nitrogen starts turning back into gas, forming bubbles and potentially causing decompression sickness. This point is called the M value. An M value represents the maximum nitrogen pressure that a theoretical tissue compartment can tolerate at a given ambient pressure. If we connect the M values at different pressures, we get what's known as the M value line. The goal of decompression is to make sure we always stay below this line and avoid decompression sickness. Earlier, we mentioned that decompression algorithms are based on theoretical tissue compartments. And since every diver's body is different, we can't simply use the M value line as our decompression limit. We need an additional safety margin. That's where gradient factors, or GF, come in. Let's go back to the chart. Now we're going to add some conservatism. We'll draw another line below the M value line and use it as our actual decompression limit. This GF line is defined by 2 percentages, GF low and GF high. GF low is on the right. If we define the M value as 100, and saturation pressure as 0, GF low is set somewhere within that range. It determines how deep your first decompression stop will be. GF high is on the left, which represents the surface. Again, the M value is 100, and saturation pressure is 0. GF high is set within that range and affects the total decompression time. Let's use Garmin's default high conservatism setting, GF3575, as an example. As we ascend, nitrogen in the tissue goes from saturated to supersaturated. Eventually we reach the GF line. We can't exceed that line, so this becomes our first decompression stop. At this point, we're at 35%. After completing the stop, we continue ascending. We reach the GF line again, make another stop, and repeat the process. Eventually, we arrive safely at the surface. At that point, we're at 75%. Now let's see how different GF settings affect decompression. First, let's compare GF4575. With a higher GF low, the first stop occurs at a shallower depth. It's closer to the M value line and therefore less conservative. Next, let's look at GF high. We'll compare GF3595. With a higher GF high, total decompression time becomes shorter. You'll reach the surface with more nitrogen remaining in your tissues, making it less conservative. You can also see that GF high affects your NDL. To change the GF settings on your dive computer, first select your dive activity. Then go to Dive Setup. Select Conservatism. From there, you can choose one of the preset conservatism levels or manually customize GF low and GF high. Next, let's talk about the GF99 data field. GF99 represents your current gradient factor. More specifically, it shows the GF value of the tissue compartment with the highest level of inert gas supersaturation among all 16 theoretical tissue compartments. Again, let's use GF3575 as an example. If you follow the dive computer's decompression schedule perfectly, GF99 will be 35 when you arrive at your first decompression stop. That's your GF low. And when you reach the surface, GF99 will be 75. That's your GF high. But what if GF99 reads 40 at your first stop? That means you're closer to the M value line than expected. Your tissues are more supersaturated than the decompression model intended. If GF99 reaches 100, it means you've reached the M value. And if it exceeds 100, you've gone beyond the M value line, significantly increasing your risk of decompression sickness. On the other hand, if GF99 displays on-gassing, it means your tissues are still absorbing nitrogen and haven't become supersaturated yet. Finally, let's talk about surface GF. Surface GF represents what your GF would be if you were to ascend directly to the surface right now without making any additional stops. It's a predictive value that helps you evaluate the decompression risk you would face in an emergency situation where you're forced to skip all remaining stops and surface immediately. GF99 and surface GF are not included in the default data screens. To add them, first select your dive activity. Then go to Dive Setup. Select Display Settings, Data Screens, Add New, Custom to, Data Fields. Pick the field you want to configure. Then select Diving Fields. You'll find GF99 and Surface Gradient Factor in the list. When you're done, just go back. And that's it. Now we have a deeper understanding of the dive computer on our wrist. Dive safe.